students, welcome to Sunil's tutorial. I'm Sunil Mirwani and today we'll be doing this chapter called as atoms, molecule and nuclei. Let's start. Now, let's come to Planck's quantum theory. Now, as per Planck's quantum theory, energy associated with electromagnetic radiation of any frequency is absorbed or emitted but not continuously but in the form of small packets of energy called as photons. What are photons? Energy can neither be absorbed continuously nor can it be given out continuously. It is absorbed and given out in the form of small packets, and these packets are called as photons. So it says that energy associated with electromagnetic radiations of any frequency is absorbed. Energy associated with electromagnetic radiation of any frequency is absorbed or emitted not continuously but in the form of small packets called photons. Right? Now, what are the properties of photons? Properties of photons. First, photons possess properties like particles. Photons possess properties like particles. Second, they have properties of waves. That means each photon is associated with a wave of definite wavelength. Have properties of waves and have a definite wavelength. Next, photons. Photons do not carry any charge. They do not carry any charge. Right? Next, they can collide with electrons in the substances. Right? They have this ability to collide, can collide with electrons in substances. Next, the energy associated with the energy of a photon with frequency V, the energy of photon with frequency V is given is E is equal to hV, where h is a constant, right? Now, h is a constant and it is called as Planck's constant. Fine. They possess momentum. They possess momentum.
So E equals to hv. What's E?
E is the energy. H is Planck's constant. It's a constant, right? Now, they possess momentum, and the momentum possessed by them can be given by the formula hv by c. And I can say that which is momentum is given by the formula hv by c. Okay. Now let's see, this was your Planck's quantum theory and the properties of photon. Now let's see Bohr's first postulate. Now Bohr's first postulate says that the electron in an hydrogen atom revolves in a circular orbit of nucleus, around the nucleus, situated at the center. Now the centripetal force, since the electron is moving in a circular orbit, it will have some centripetal force. The centripetal force required for the circular motion is provided by the electrostatic force of attraction between the positively charged nucleus and the negatively charged electron. Why is it continuously moving in the circular orbit? Because of the electrostatic force between the positively charged nucleus and the negatively charged electron. Fine. Bohr's first postulate says that the electron in a hydrogen atom, revolves in a circular orbit around the nucleus. In a circular orbit around the nucleus. The centripetal force required for this circular motion is provided by the electrostatic force of attraction between the positively charged nucleus and negatively charged electrons. Fine. Now, in a hydrogen orbit or in a hydrogen atom, there is only one electron revolving in a circular orbit around the nucleus. Since the atom is electrically neutral, the magnitude of the positive charge on the nucleus should be equal to that of the electron. Now let us assume that this is my hydrogen atom, this is my nucleus. Let's assume that the radius of the orbit is r, right? And you have an electron revolving here. This is my electron that is revolving. It has a linear velocity of v, and you have a positively charged proton at the center. Now if r is the radius of the orbit, then I can say that the electrostatic force of attraction will be can be calculated by using Coulomb's law. I can say that since the atom is electrically neutral, the magnitude of the positive charge in the nucleus, of hydrogen atom is equal to the charge on the electron. Now let us assume that let r be the radius of the orbit. Let r be the radius of the orbit. if r is the radius of the orbit, then the electrostatic force of attraction between the positively charged nucleus and the negatively charged electron can be given by Coulomb's law. Then the electrostatic force of attraction can be given by Coulomb's law. What does Coulomb's law state? F is equal to 1 upon 4 pi epsilon 0 E square upon R square. It should be Q1, Q2, but we just said that the charge on both the proton and the electron is the same and the distance is R square. Now this electrostatic force serves as the centripetal force necessary for the circular motion. I can say that this electrostatic force serves as centripetal force for centripetal force necessary for circular motion. Centripetal force necessary for circular motion, right? Circular motion of the electron round the nucleus. Right? Now, if m is the mass and v is the orbital speed of the electron, if m is mass and v is orbital speed of electron, then centripetal force acting on the electron is given by centripetal force is mv square by r. But we said that the electrostatic force provides the necessary centripetal force, therefore I can say but electrostatic force is equal to the centripetal force, therefore I can say that 1 upon 4 pi epsilon 0 E square upon R square is mv square by R, right? That is my equation for Bohr's first postulate. Next, let's see Bohr's second postulate. Let's see Bohr's second postulate. It says that an electron can revolve without radiating energy only in those orbits for which the angular momentum of the electron is equal to the integral multiple of h by 2 pi. See, we said that any body cannot radiate or absorb energy continuously, but it will move continuously in a particular, if an electron is at a particular distance from the nucleus, then it can move continuously without absorbing or without radiating energy. And what should that distance be? That distance should be an integral multiple of h by 2 pi. Only if that distance of the electron from the nucleus is an integral multiple of h by 2 pi, then it can move around the nucleus without absorbing or radiating energy, which is synonymous to a car moving in a neutral gear. When a car is moving in a neutral gear, it is not consuming any energy from the petrol tank, it is just moving on inertia. So exactly synonymous example is that. So I can say that the electron can revolve without radiating without radiating energy only in those orbits for which the angular momentum of the electron is equal to an integral multiple of h by 2 pi. So only when it is, if the angular momentum is an integral multiple of h by 2 pi, only then the electron can revolve in the orbit without radiating or absorbing energy. Now let us assume, let omega be the angular velocity. Let's assume that omega is the angular velocity of the electron in circular orbit, right? Then I can say that the orbital speed of the electron v will be equal to r omega, right? Therefore I can say that omega is nothing but v by r, right? So I'll come to know the angular velocity. Now if I is the moment of inertia of the electron, then I can say that I is equal to mr square by basic definition of moment of inertia, right? Angular momentum is given by the formula I omega, right? I we found out is mr square, right? Omega we found out is nothing but v by r. Therefore the angular momentum is going to be mvr, but by Bohr's second postulate, angular momentum should be an integral multiple of h by 2 pi. That means mvr is equal to nh by 2 pi. That's my equation for second postulate of Bohr's theory, right? Now, so next, so these orbits where the electron can revolve without absorbing or radiating energy are called as stationary orbits. Okay. Next, Bohr's third postulate. Bohr's third postulate says that an electron radiates energy only when it jumps from an orbit of higher energy level to an orbit of lower energy level. If an electron jumps from an orbit of higher energy level to that of a lower energy level, then that difference in the energy is going to be radiated, right? So I can say that an electron radiates energy only when it jumps from an orbit of higher energy level to an orbit of lower energy level. From an orbit of higher energy level to an orbit of lower energy level. The energy radiated is equal to the difference between the energies of the orbit in the two energies of the electron in the two orbit. How much energy is going to be radiated? The energy radiated is equal to the difference between the energies the difference between the energies of the electron in the two orbits. Fine. Now this energy is radiated in the form, the energy is radiated, but how is it radiated? It is radiated in the form of photon energy. It is radiated in the form of photon energy. The energy is radiated in the form of photon energy. The energy is radiated in the form of photon energy hv, right? Where h is Planck's constant and v is the frequency of radiation. Where h is Planck's constant and v is the frequency of radiation. Fine. So do you understand? So do you understand Bohr's second postulate, right? Next, once you have this, so let's see this. Let's assume that according to this postulate, En is the energy of the electron in the initial or the higher orbit, and Ep is the energy of the electron in the final orbit. If En is the energy of the electron in initial orbit, which is your higher orbit, and let's assume that Ep is the energy of the electron in lower orbit or final orbit, which is your lower orbit. So in which case I can say that by this postulate En minus Ep should be equal to hv. Fine. That is my Bohr's third postulate. Now let us try to find out the radius of Bohr's orbit. Radius of Bohr's orbit. Right? I can say that in Bohr's model, the electron can revolve in those orbits where the quantum condition is satisfied. Such quantum selected stationary orbits are called as Bohr's orbit. So what you call as stationary orbits are also called as Bohr's orbit. What are stationary orbits? These are those orbits in which the electron can revolve without absorbing or radiating any energy. Fine, do you get this thing clear? Okay, now let's try to find out the theory. According to Bohr's first postulate, I can say that centripetal force is equal to electrostatic force. Centripetal force is equal to electrostatic force. Centripetal force is nothing but mv square by r. Electrostatic force 1 upon 4 pi epsilon 0 e square by r square. Right, that's Bohr's first postulate. Therefore, I can say that v square is nothing but e square upon 4 pi epsilon 0 mr. Right? That is as per Bohr's first postulate. Now, according to second postulate, I can say that MVR is NH by 2 pi. Therefore, I could say that if I square both the sides, I'll get m square v square r square is n square h square by 4 pi square. Fine. So in that case, I will get v square is nothing but n square h square upon 4 pi square m square r square, right? From Bohr's first postulate also I got v square, from Bohr's second postulate also I got v square. Therefore I can say, equating the two equations, if I equate the two equations, I'll get e square upon 4 pi epsilon 0 mr is n square h square upon 4 pi square m square r square. So mn square gets cancelled, rn square gets cancelled, 4 and 4 gets cancelled, pi n square gets cancelled. So that leaves me with r is equal to n square h square epsilon 0 upon pi m e square, right? That is going to be my radius of the Bohr's orbit. Right? Done. Now in this expression, we know that I can rearrange this expression and write this as epsilon 0 h square upon pi m e square into n square. Now here epsilon 0, h, pi, m and e are all constants, right? The only thing that changes is the orbit number. Thus I can say that r is directly proportional to n square, right? That is my expression for radius of Bohr's orbit. Next, let's try to find out the energy in Bohr's orbit. Now, energy, the total energy possessed in Bohr's orbit is going to be the sum of its potential energy and kinetic energy. Now, first let's find out the kinetic energy of the orbiting electron. Kinetic energy of orbiting electron. Now, according to Bohr's first postulate, according to Bohr's first postulate, I can say that mv square by r is equal to 1 upon 4 pi epsilon 0 e square by r square. So in that case I can say that mv square is e square upon 4 pi epsilon 0 r, right? And kinetic energy we know is nothing but half mv square. So I can therefore say that this is going to be mv square can be substituted. So that will be e square upon 4 pi epsilon 0 r. So kinetic energy is going to be equal to e square upon 8 pi epsilon 0 r. That will be the kinetic energy possessed by the electron in Bohr's orbit. Now let's find out the potential energy possessed in the Bohr's orbit. Potential energy in of orbiting electron, right? Now the electron inside the atom is at a distance of r from the nucleus and carries a charge of E. I can say that the electron inside the atom, electron inside the atom is at a distance of r from the nucleus carrying a charge of plus E. The nucleus is carrying a charge of plus E. Now let's assume that the electric potential is V. Let capital V be the electric potential. If capital V is the electric potential, then I can say V is 1 upon 4 pi epsilon 0 E by R. That's the formula for electric potential. Now, by definition, electric potential represents the potential energy of unit charge at a distance of R from a charge plus E. What is electric potential? By definition, a potential represents the potential energy represents potential energy of a unit charge at a distance R from a charge of plus E, right? That means I can therefore say that potential energy of an electron at a distance R can be given by potential energy of an electron at distance R is given by potential energy is nothing but the electric potential multiplied by the charge on the given substance. I just gave you the definition that potential energy is nothing but electric potential into the charge. Electric potential is 1 upon 4 pi epsilon 0 E upon R into minus E. So this is going to be nothing but minus E square upon 4 pi epsilon 0 R. That will be the potential energy, right? Next, once I know the potential energy, then I can find out the total energy. Total energy of orbiting electron. We know that total energy is sum of potential energy and kinetic energy. Potential energy is minus E square upon 4 pi epsilon 0 R. Kinetic energy we found out is E square upon 8 pi epsilon 0 R. This can be written as E square upon 4 pi epsilon 0 R common. So minus 1 plus 1 upon 2. Right? So in that case, this will give you minus 1 upon 2. So this will be minus E square upon 8 pi epsilon 0 R. So the total energy of an orbiting electron is minus E square upon 8 pi epsilon 0 R. But we know that the radius is nothing but, we have derived an expression for radius. We said that radius is epsilon 0 h square upon pi me square into n square. Substitute the value of radius here. If I substitute the value of radius, I will get total energy is minus E square upon 8 pi epsilon 0 h square n square upon pi me square. Right? Pi and pi gets cancelled. So in that case, this is going to be nothing but total energy is going to be minus me4 upon 8 epsilon 0 square h square n square. Right? Now here again I can say that therefore total energy is equal to mass of the electron is constant, charge on the electron is constant, 8 epsilon 0 square h square is constant into 1 upon n square. Thus I can say that since minus me4 upon 8 epsilon 0 square h square is constant Therefore, you can say that E is inversely proportional to 1 upon n square. Right? That will be the expression for total energy of the electron. Now, let's find out the numerical value of the total energy of the electron in Bohr's orbit. I can say, but m, that is your mass of the electron, is nothing but 9 into 9.11 into 10 raised to minus 31 kgs. Then E, that is charge on electron, is nothing but 1.6 into 10 raised to minus 19 coulombs. Next, epsilon 0 is permittivity of free space, which is nothing but 8.85 into 10 raised to minus 12 coulomb square for Newton meter square. And H is Planck's constant, which is nothing but 6.63 into 10 raised to minus 34 joule second. All these values are constant. If I substitute in the equation, the equation E is equal to minus Me4 upon 8 epsilon square 0 square h square into 1 upon n square, you will get the value of E to be 21.7. If I substitute all the values and solve, 21.7 into 10 raised to minus 19 upon n square joules, that will be the energy that will be present in an electron which is in the nth orbit, right? But we know that 1 electron volt is nothing but 1.6 into 10 raised to minus 19 joules, right? Therefore, I can say this should be minus. So E is minus 21.7 into 10 raised to minus 19 upon 1.6 into 10 raised to minus 19 into 1 upon n square electron volts. When you divide this, you will get this as minus 13.6 upon n square electron volt. So the total energy in an orbit n of Bohr's electron or Bohr's atom is going to be minus 13.6 upon n square electron volt. Fine, do we get this thing clear? Right, we'll stop this here for the day. Thank you very much.